Hi everyone. So today we are going to solve one of the code shift problem, and that problem is compressed list. So what the problem is that we'll see in a while. I just try to capture a summary of that problem first. So let's go through the summary first, and then we'll see what the real problem is and the sample test cases. So we're given a list. Let's say we have a list 1. And it consists of elements like 1, 2, 3, 5, 6, 8, 9, 10, 11, 12, 15, 17. It's just a random list. It could be big, it could be small. And the requirement is to compress it. And how the compression needs to be done, how the compression needs to be done is that the contiguous elements which are more than 2, which means like 1, 2, 3, we have 3 contiguous elements. If they are more than 2, they need to be separated by a dot. It becomes 1, 2, 3. 5, 6 are only 2 contiguous elements, so it will be 5, 6. 8 to 12, it's 8, 9, 10, 11, 12, which is 4 contiguous elements. It will be 8 to 12 because it's more than 2. 15, 17 will remain as it is. So it says that contiguous elements greater than 2, not greater than equal to, greater than 2, separated by a dot. With first and the last, means 1, 2, 3 will be get replaced by first, 1 dot dot 3 means 1 and 3. Similarly, 8, 9, 10, 11, 12 will be replaced as 8 and 12. 15, 17 will remain as it is because they are not contiguous. This is one sample space. Another sample space, 4, 7, 9, 11. Here you have no contiguous elements. They will remain as it is after the compression because they cannot be compressed. So this is a brief summary of the problem, which I have tried to capture first. And now let's take a look of the entire what the code shift question says about. And we'll go through the question in detail. We'll see what are the sample input test cases, sample output, and then we'll again come back and try to solve it as a pseudocode first before going for live code. Okay.
Now let's have a look at this problem and compress the list from the code shift. So what this problem states? This problem states is that you are given a strictly increasing sequence of integers a1, a2 to an. This is as we saw on the whiteboard summary of the problem that we have a list of integers and they are in the increasing order. And our task is to compress this sequence. Now this is something very important, the next para. The compressed form of the sequence is a sequence of ranges separated by commas. A range is either an integer or a pair of integers separated by 3 dots string. So for the ranges, which we discussed, it will have only the first element and the last element which are separated by 3 dots. When each range A to B is in the compressed form, is decompressed into the subsequence A plus 1, so on, till B, which should obtain the comma separated sequence A again. For each maximal contiguous subsequence of A such that B is greater than or equal to A plus 2, the compressed form of A must contain the range A to B. If B is less than 1, shared sequence should not be compressed into a range. Our contiguous subsequence is maximal if it cannot be extended by at least one element of A next to it. It can be proved that the compressed form of any sequence is unique. So this is what the problem statement is saying, and we saw this only in net loud. After going through the problem statement, let's take the examples of how it is going to. That will give a more clear picture. Let's say we have an example input of sequence 1, 2, 3, 5, 6, 8, 9, 10, 11, 12, 15, 17. It will be compressed into 1, 2, 3, 5 and 6, 8, 8 to 12, 15, and 17. And one more example, 4, 5, 7, 8 will remain as it is. There won't be any change in there. So If we see the explanation part, 1, 2, 3 is a contiguous subsequence with length greater than 2, which means 3, so it will be replaced by dot. 5 to 6 has length only 2, so there is no point of compressing it into a range, because even if we write 5 dot dot 6, it won't make any sense. 8, 9, 10, 11, 12 is a perfect candidate for compression, so it will be replaced by 8. Element 15 and 17, no change. So this is a problem. Let's now move to the solution part. We'll think about the solution on the whiteboard. If you want to think on your own, you can pause this video over here and spend some time on it. And we'll go to the solution on the first whiteboard first, then we'll have go through the code.
So let's start our whiteboard exercise on this problem. So as we have seen, the input is 1, 2, 3, 5, 6, 8, 9, 10, 11, 12, 15, 17, and we have to compress this. And after compressing this, it will become 1, 2, 3, 5, 6, 8 to 12, 15, and 17. So if we go by the brute force solution, it will be like creating a sub-array of each and checking around whether it's a contiguous or not, and then checking its length, and then trimming it down. So since we are creating a sub-array, a brute force will always take over square in this case. Let's discuss the optimized solution over here. And brute force you can try it on your own, and if there is any issue, then we can discuss it. For the optimized based solution, where we have to do it better than ON square, which means in the order of ON, there is in case of arrays, there is a pattern which is known as window-based pattern or a window-based solution, which means that instead of going for finding any sub-array, we maintain 2 pointers. We maintain a window, and we'll start and we'll move that window across and shrink it and across. So that will be a dynamic size window, which will be start moving on this array, and it will cover the entire array. So how we do it? Let's see that. We'll take 2 pointers, which is window end and window start. Initially, both will point to the start. We'll have a look at very carefully how we are going to move this. We'll check whether this element and the next element is incremented by 1, which means the difference of this element and the first element is 1. Then we'll increase our window, means we'll take that element into our window. So we'll increase the window, we move the win end from here to win end. We have landed here. Now again we'll check the next element, which is 3, is again 1 plus from the current element. If yes, we'll increase the scope of our window end and we'll move it here. So what we are doing, we are basically checking the current element and the next element. They are in a difference of 1, means they are contiguous or not. Now we'll see the next. The next is 5, which is not 1 plus. We are breaking the sequence over here. So this will be a check condition or a base condition, or I would say a validation condition. Here our window needs to be changed, window needs to be stopped. So what we'll do first step, we'll check what is our window size. Our window size is window end minus window start, which is greater than 2. Since it's greater than 2, it has fulfilled our compression funda. So we'll make it a sequence 1 dot dot 3, and we'll move our window start and window end both over here. Alright, so let me give a brief recap again. We started from here, window start and window end. We move one by one, window end. It means we are expanding our window. It's just like a frame. You can think of a frame. We are expanding our frame, taking the next element. If it fulfills the condition, then again taking the next element. If it fulfills our condition, we do keep on checking unless and until we get something which blocks it. The moment we get a blocking element, we'll check how far the frame size has become, which means this is the frame size. If the frame size is greater than 2, Then we'll make it a pattern and we'll take the first and the last before resetting our pointers, and we'll just store it as a result somewhere, and then we'll move ahead. Again we'll move ahead, window start and window end. We'll come to 6. It is fine, no head. We'll again move the window end, which is 8. Now when we come here, we see that this is blocking our order. So we will check what all we have encountered so far. Its length, window end and window start, which is not greater than 2. So we'll simply put the element as it is, 5, 6, and we'll make our window start as next. And we'll again start from here, keep on moving 9, 10, 11, 12. We'll get the window end over here. Put it as a sequence, 8, 12. Move it further. And at the last, we'll get the elements, they are non-contiguous as it is. So basically what we are doing, the main principle or the main fundamental here is that we are creating a small window or a frame, and we are moving that frame one by one if our condition fulfills of that frame. And as soon as we get our terminating conditions, we stop our frame, store the result somewhere and move ahead. So that is the principle of solving it at ON, because we are moving this small window, the small frame across our entire array, which is ON. So the complexity of the solution is ON. Time complexity, this is time complexity. Space complexity will be like, it is around the window size, the max window size which is happening. That is the space complexity which we have. That could be, you can say O of k, or you can say of the order of O of n only. But still k is very, very less than n. But the main point is we are not creating any severity. We are not having the complexity of O n square. We are simply migrated to O of n. So that is why it's a better and optimized solution of it. Alright, so this is a high level algorithm, pseudocode. We'll now move to the coding part and we'll see that how is it being done over here.
So after going through the problem, let's have a look at what the code will be of this problem like. So we have gone through the whiteboard solution of it. We have the pseudo in our mind, and now we have to just draft it algorithm into the code and run it. So we are using IntelliJ and Java for it. So let's see how it goes. So we have a sample array which is 1, 2, 3, 5, 6, 8, 9, 10, 11, 12, 15, 17. And we have just simply written a method which will take an array. So as I explained in the solution, we are following a window-based approach, which means it's a frame which will keep on moving from left to right and cover the entire array, and will give us an ON complexity. So for initial time, I will initialize the start of the window as 0 and the end of the window as 1, which means the first element is there in the frame. Now we have to expand that frame or compress that frame based on the conditions it fulfills or not. So how we are doing it? So we'll create a while loop where we check whether the window start is less than or equal to window end, which means that our window frame does not expand in the reverse direction, and we need to make sure that we run till the arrow length. So we'll check whether we are following the sequence or not. So this method, this code, just validates. What it does is that it validates whether we are following the contiguous subsequence. If our previous element is 1 plus, the current element will keep on incrementing the count and keep on increasing the frame. There is no point of going ahead or going to some other condition. If the condition is not met, then we move out. And after we move out, we currently will check how far we have executed, how far we have got a frame. This count will indicate what is my frame length. If my frame length is greater than 2, it means that it's a very valid candidate for compression, and we need to compress it. How we compress it? We'll simply append to a string buffer and we'll take the first and the last element -1. Why I'm saying -1? Because at the time this condition will be violated, my pointer will be one step ahead of that element. So that is why I need to go back and take that element. And after appending it, I will make the frame restart. I will make the window start equal to window end and increment the window end by 1. So this will be how I'll compress it. Means when we have more than 2 elements. If there is no 2 elements are there, which means that there are no contiguous subsequence, we'll simply append those 2 elements. The element as it is. Won't change anything and just simply do it. The same thing will be done when we have count 0. When it's totally unique elements happening across and there is no relation, they are having a big difference between them. So in short, there will be 3 cases. The first is the one where we have a sequence of more than length 2, then we have sequence of length 1, then we don't have any length. So let's try and run it, and then we'll of course debug it to understand how it's working. So the reason why I want to debug and show the code is that because debugging is a very essential step and shows you step by step how the code is happening, and it gives you a very good explanation of the problem and its solution. So see, the input is 1, 2, 3, 5, 6, 8, 9, 10, 11, 12, 15, 17, and its output as 1, 2, 3, 5, 6, 8 to 12, 15, 17. And 4, 7, 9, 11 will remain as it is. This is what it is. Let's try and debug. So initially when the window start is 0, window end is 1. I check window end -1, which means that error 0, first element +1 is equal to error 1. Yes, it is 1 + 1 is 2. So this means that this is a valid pair 1 and 2. We'll increment the window size, which means that we'll increment the frame set counter and also move the frame by 1. Continue, which means that we'll move to the next element. Next element is 3. So 3 minus, which means that this previous element 2 + 1 is equal to 3. Okay, so this is again a valid sequence. So at every step we are checking. First we check 1 and 2. In the next iteration we are checking 2 and 3. So you see, when we check 2 and 3, it fulfills the category of a valid pair, and we move the window end pointer again by 1. And we again do a continue. Now when we do a continue, we land up at 5. So if you see, window end is currently 3, which means that it index 3 is element 5. Index, the element 1 is 0, the element 2 is index 1, the element 3 is index 2, the element 5 is index 3. So we come to the next condition of checking the counters, which we have incremented in the earlier step, and we see that the counter is 2. Okay, so we create a compression string by taking the window start and window end -1. Because why -1? Because we are currently our window end is pointing to 5. We need to go back one element and append it. And the last, we increase the window end by 1. We make it 3. And then again come here. Which means that we are now checking 5 and 6 onwards. We check this 5 and 6. We check, yes, they are a part of a sequence. We make the window end as 4. Continue. Now we get as 8, 8 does not fulfill. So we get the count as 1, and here we just append from window start to window end, make it into comma separated. Make the count as 0 at each and every step where we are checking the counter. We need to make the reset the counter. These are the steps for resetting the counter. If you see here, here is already 0, so there is no point of resetting it. But we are resetting the count over here, making the window start as window end, again incrementing the window end by 1. After 5 and 6, we are now left with 8, and this iteration will continue for 8, 9, 10. See, ultimately we'll land up to count is 4, which means where we have 8, 9, 10, 11, 12. We are till 12. We have reached till 12. So we'll append the window start and window end -1 and create a buffer string. We can return it. And after that, we process the 15 and 17, which are the remaining elements, which will go over here because they have count as it. So in this way, we have completed this entire array and compressed it, and the final result we have it as. Let's go to the console and we'll see 1, 3, 5, 6, 7. Now, when we take an array like which is not even contiguous 4, 7, 9, 11, it will all go into the condition where count equal to 0. If you see, it will always go into the count equal to 0. So in short, if we go and analyze this code, what we have done is that we have simply taken a frame, window start, window end. We have simply iterated, taken a frame and try to move that window on this entire array. And then we are comparing the elements one by one. And the main important part is how to handle the counts. There can be elements which are contiguous. There can be only 2 elements which are contiguous, or there can be elements which are not even contiguous. We have handled the 3 cases over here, which form the basis of our compression. So you can say this code is for the compression part, and this code is for the defining the basis for the compression part. So the time complexity will be O(n). The space complexity will be this frame size, which depends on how big the frame can go. But this is efficient than than forming sub-arrays of O(n) square and just trying to check each and every time. So this is the code part of this solution. I'll post this code on the GitHub so that you can have a look at it and you can run it on your own.
So finally, we have solved one more problem of CodeShip, which is compression of list. So the approach, just a brief recap of the approach we followed. We first went to the problem summary, we saw the problem in detail, what the problem states, and before jumping onto the code, again we followed the principle of doing a whiteboard analysis or a basic pseudo algorithm analysis of that. This really helps in shaping up the solution which you get, final solution, so that whenever we are coding it, we are into more confidence into the code. We know what we are writing it, and we can handle the corner cases like how the window frame is changing, how the windows start and the window end where variables are initialized, how they are used, how they are propagated across. So these are some key pointers which you first look around while you are building up the solution, and then while you implement it, it gets a bit more refined. So this is an interesting approach of solving a problem, and I feel that this should be the approach while you're doing any computer programming, or you're solving any problem in your day-to-day life, in your college, in your studies, or in your work assignments anywhere. So guys, that is it. In case like you like it, just please give some comments, or if you want to see any new problem or anything, please feel free to comment it and give some feedback, anything. So thanks for watching this video, and we'll come up with new problems. And not only problems, I'm thinking of putting up some concepts, some designing concepts and all. So stay tuned and keep watching. Thank you.